flight on mission.
Go flight.
Please confirm FTS is green on internal power.
FTS is green and go for flight.
And all stations, this is flight on mission. From now there should be no red flags on your LCCs.
FSO RCO mission court. Confirm flight safety is green.
Flight safety is green.
All stations on mission, range is green, auto sequence is armed.
And to all operators, we are go for auto sequence start at T-minus 2 minutes.
Galley's running.
Reading GNC systems.
10, 9, 8, 7, 6, 5, 4, 3, 2,
Ignition.
1.
Well, it's been a busy few years. And you'll notice we measure things in days at Rocket Lab, not months or years. So what have we accomplished in the last 1,800 days roughly? So we started off developing a Rutherford rocket engine. We've put 70 of them into space now. Last month, the 100th engine came off the production line. And I'm just incredibly proud of the propulsion team for the engine that they've created. The first all 3D printed engine, first electric turbo pump cycle. There's a lot of innovations in that engine. And then there's Electron itself. As you saw from the video, we've been to orbit 7 times. There's one on the pad right now. In fact, we just finished the wet dress of that vehicle yesterday. And the vehicle itself is proven to be 100% customer deployment success. And we're really proud of the orbital insertion accuracy that we were able to achieve. Where average insertion accuracy is around about 1.4 kilometers, and for you guys, I know that's pretty helpful. We're able to give state vectors to our customers within 20 minutes, and they're able to find their spacecraft straight away. There's no looking for spacecraft in a sea. So we also built a launch site. This is LC1. In order for us to build this launch site, it required a bilateral treaty between New Zealand and America. New Zealand government had to create a whole lot of laws, then they had to create a space agency, and then the Aussies got jealous and they created a space agency too, so we created 2 space agencies. But nevertheless, there was a massive feat. We have tracking stations all around the world: Cork, Azores, Chatham Islands, Southland Australia. And the site is licensed to launch every 72 hours for the next 30 years. So we have more launch frequency out of that site than most countries. And then there's LC2. We're incredibly proud and working with the team at Mars to develop LC2. I think it's going to go down as the fastest launch pad build in history. We started driving piles in January, and that site's going to be activated before the end of the year. And that'll give us even more launch frequency. And then there's production. Production's way harder than anybody thinks. Production is super hard, and we've developed over 4.5 acres of new factories, both in New Zealand and here in the US, to try and get to 1 rocket a week. We're not there yet. We're launching every 30 days, roughly right now, and some areas of the company are producing their components within every 20 days. So we're marching really, really quickly to every 2 weeks, and then every week. But massive amount of infrastructure build in factories globally. And then there's Photon. And Photon I'm really excited about because launch for a very long time has been the bottleneck, the really big barrier to get ideas and innovation on orbit. And I think we're starting to get close to checking that box. The next big hurdle for anybody to get innovation and ideas on orbit is you have to go and build your own satellite bus. And that's a very time and expensive exercise. And the whole point of Photon is to remove that barrier. Really, we think of it like a sandbox in LEO, where you don't have to worry about all the satellite bit. You just come with your innovation, come with your payload or your sensor, and all of that other stuff is taken care of. And there's a launch vehicle attached to it to boot. So no more looking for trying to source a satellite, then try and source a launch. It's all one package. And really, it drives, all of these things drive to really this statement, and we live and die by this statement at Rocket Lab. We do what we say we're going to do, and you'll see throughout the history of the company, very, very rarely will we make an announcement where we're not really far along or already done. The kick stage, we kind of got busted with the kick stage because people started tracking 2 things on orbit, so we had to announce that one. But the kick stage and then Photon, the first commercial Photon is going on orbit by the end of the year, and we already have 5 Photons on orbit in early stages from all the missions that we have flown. So generally, I think that's the sense that Rocket Lab we do what we say we're going to do, and we certainly try to. So this is a Rocket Lab cap. This is a cap that I'm about to eat because I've said publicly a few times the various things that Rocket Lab would never do. So unfortunately, I find myself in the position of eating my hat. So I'm an engineer at heart. I'm the chief engineer for the project, and really, from day one, it's always been about engineering for me, and I love building beautiful machines. In fact, I love beautiful machines all round. And throughout history, there's rare occurrences where a beautiful machine really changes the course of human history. And I selected this picture here because it's a printing press. And before a printing press, you would have to write each individual article. And really, a printing press democratized information. A printing press, all of a sudden, you didn't have to have a one handwritten bespoke thing. You could take that one handwritten bespoke thing and mass produce it and distribute it to the knowledge to the world. So I very much love beautiful machines, and this is a great example of a beautiful machine. If you look at those involute gear tooth profiles, they're just absolutely lovely. But even I have to admit, it would be pretty silly to print one piece of paper and then throw this beautiful machine away. So Electron is going reusable. So let me explain why I thought this was impossible. So we have a terminology within Rocket Lab that we affectionately call the wall. And the reality is we're not doing a propulsive re-entry, and obviously you saw we're not doing a propulsive landing. And the fundamental reason for that is that takes a small launch vehicle and turns it into a medium-sized launch vehicle. And we're not in the business of building medium-sized launch vehicles, we're in the business of building small launch vehicles for dedicated customers to get on orbit frequently. So a lot of things don't scale well, and that's one of the things that really don't scale well in a small launch vehicle. So we have to start off at 8.5 times the speed of sound, and we have to get down to 0.01 times the speed of sound in around about 70 seconds. And that's a really challenging thing to do. There's a lot of energy that needs to be dealt with on the way down. So we need to dissipate around about 3.5 gigajoules of energy. That's a lot of energy to deal with on the way down. And to put it into more context, 3.5 gigajoules powers 57,000 homes for an instant. That kind of gives you a sense of how much energy that we have to scrub, and we can't scrub that propulsively. And when we're entering, we generate a lot of shock waves and shock-shock interactions, and the plasma around those shock waves is equal to about half the temperature of the sun. So we have tremendous aerothermal loads. I think you can probably see by now why I thought this was a pretty big challenge prior to this. And then the aerodynamic loads, it's like taking an Electron and standing 3 elephants on the top. So you have a 1.8 millimeter carbon fibre rocket with 3 elephants standing on the top with heating loads half the temperature of the sun, re-entering the Earth's atmosphere at 8.5 times the speed of sound. And we've got to get it down safely and in one piece. So there's lots of really big challenges here to try and deal with. So why did we convince ourselves, how do we convince ourselves this was possible? Well, we started flying, and when we started flying, we started getting more and more data. The Electron is basically a flying laboratory. We have around about 15,000 channels of data every flight. So we collect a huge amount of data every flight, and once you start to collect that data, we started to build these computational fluid dynamic models, and we tried to understand and close the verification loop of what's going on. And what you see there is a CFD model of a stage at the beginning of re-entry. And then you can see the kind of flow fields you get as you're trying to re-enter here, and the kind of interactions with the vehicle and the atmosphere. This is a particularly interesting CFD plot. This shows all the shock-shock interactions. So when you produce one of those shock waves, which is white, just think of that as the sun, or half the temperature of the sun. And you'll notice a few of those shock waves on this particular angle of attack of re-entry at 10 degrees are attaching themselves to the launch vehicle. That is a plasma knife. So that is a very difficult thing to deal with, both from a TPS perspective, but also from a re-entry control perspective. So this is a hard problem, and we're taking a completely different approach to solving this problem. We're doing it very, very passively. We're doing it with a lot of TPS and a lot of aerodynamic decelerators to try and push our way through that boundary wall. So if we think about what is our plan here, we started flying in earnest, commercially end of last year, and that's when we started to gather data. And more recently, we've really started to nail down on this. So Flight 6, we gathered a lot of data. Flight 7, we gathered even more data. This Flight 8, this coming up, that's on the pad, is a really critical flight. So this Flight 8 has an advanced data recorder system that we've named Brutus, and it's named Brutus because really, Brutus rides the stage all the way through atmospheric re-entry, all the way through those regimes, and the stage will break up, and it's going to ride that stage all the way down and splash into the ocean. Then we're going to pick that thing up, and it's a super high fidelity data recorder, so we'll have a lot more understanding of the environment. And then we can use all that information to validate our CFD models and all of our other trajectory models. And for Flight 10, we have a major upgrade for Electron. So there'll be some pretty major changes on Electron. But if you're flying on us, don't anybody panic, because all of these upgrades are completely standalone to Electron. They don't interface with any of the current flight systems. They're all passive. So although we're adding new systems to the vehicle and experimenting, they certainly do no harm systems. And then you'll notice that I put Flight N on there for the first recapture. And I'm reluctant to name a flight because we still have to get through the wall. And then the goals here, we've kind of broken this up into 2 main goals. Goal 1 is just to get through the wall. And I bet a lot of you guys were sitting there watching and looking at the helicopter piece thinking, whoa, that's tricky. But as a budding helicopter pilot, I can assure you that is the least bit that I'm worried about. That bit is super easy. Getting through the wall is really, really hard. We've developed quite a lot of new technologies and new techniques to be able to manage this. So we think we've got a really good shot at making this happen. And then once we're through the wall, well, we go and pick it up. The ideal scenario here is, as everybody's aware, Electron is an electric turbopump vehicle. So the grand goal here is if we can capture the vehicle in wonderful condition, in theory we should be able to put it back on the pad, charge the batteries up, and go again. That's the main ideal goal. So why do this recovery? Why the change, and why are we trying to attempt this? And it comes down to this fundamental fact. Launch frequency is the absolute key here. Launch frequency is the thing that is going to change this industry, and quite frankly, going to change the world. Because if we can get these systems up on orbit quickly and reliably and frequently, we can innovate a lot more and create a lot more opportunities. So launch frequency is really the main driver for why Electron is going reusable. And in time, hopefully, we can obviously reduce prices as well. But the fundamental reason we're doing this is launch frequency. Even if I can get the stage back once, I've effectively doubled my production ratio. So that's a wonderful place to be. So thanks very much for everybody turning up, and thanks for everyone watching this live. If for the people here at SmallSat, it's time to party. So please come to the Rocket Lab party, and we'll celebrate this. But thank you very much.